All right, here we are with part 2 of the 1.9 notes. Uh, so here's the definition of an onto linear transformation and a definition of a one-to-one linear transformation. And I just want to warn you, these concepts confuse the heck out of a lot of students. I don't know what to do about it. I'm going to try to explain it as clearly as I can in as many different ways as I can. But just be aware that this might confuse you, and you might have to come back to it and try to think about it a different way later. All right, so a transformation is onto if and only if every B in Rm, remember, is the codomain here. So if everything in the codomain is the image of at least one x in Rn. So in other words, the range of an onto function is the entire codomain. So when we say the image, remember that means the output. If every b in the codomain you can get to by doing t of x for at least one vector x. And the code, so the range is a set of all of the actual outputs that you get. So another way to say that is for every b, the equation t of x equals b is consistent. And of course, we know that t of x equals b is the same as a times x equals b for some matrix A, like we've been talking about. Now, a matrix is one-to-one if and only if each b in Rm, each b in the codomain, is the image of at most one. So that means there could be 0 x's that make t of x equals b, or there could be one vector x that makes t of x equals b, but there can't be two different vectors, like x and y, that makes t of x equals b and t of y also equal to b. That's not one-to-one. Another way to say that is in terms of equations and solutions of equations. The equation t of x equals b has a unique solution, meaning one vector x that works, or no solution. But to be onto, you could have one or two or three solutions, but not 0 of this thing. So that's the main difference. Now, you've already talked about one-to-one functions in calculus, so let's look at some of those basic kinds of calculus functions. You probably haven't done onto before, but that's okay. So if we have f of x equals x squared, the graph of it looks kind of like this. And so the domain is all real numbers here. The codomain is all real numbers there, the whole y-axis. So let's check if it is onto first. If it's onto, then that would mean that everything we pick in the codomain, every y coordinate, is the result of doing x squared for some x. I just zoomed in so I can write a little bit neater. So yeah, for every y in the codomain, is y equal to f of x for some x in the domain? And the answer is no. For example, -3, if you try to make -3 equal to x squared, it's not going to work. So -3 is not equal to x squared for any x. So that means it's not onto. If we want to ask, is it 1-to-1? By the way, I abbreviate 1-to-1 like this a lot of the time, because I got to write it a lot. So if it's 1-to-1, that means for each b in Rm, or in this case, each y in R, is that the output from at most one x. And the answer to that is also no. If you take a y like 4, for example, 4 is equal to 2 squared, and 4 is also equal to -2 squared. So the equation 4 equals x squared has more than one solution. So that, and if you can find at least one value of y where that happens, then it's not 1-to-1. So the answer to this is also no. It's not 1-to-1. Okay, so let's look at g of x equals e to the x. I'll draw a graph. The graph looks like this. Is it onto? So again, this is a R to R function. The codomain is R, and we don't get every single number out. The range is really just the positive numbers. Just positive real numbers are what you can get out. So the range is not equal to the codomain. There's no way to get negative numbers from this. So this one is not onto. And you only need to find one value of y in the codomain, one real number, that is not equal to e to the x for any x. Another way you could say this is you could say that the equation y equals e to the x is not consistent for all y in the set of real numbers. There's going to be some values of y that make it so when you plug it in there, you cannot find an x that makes it true. Okay, now is it onto? Meaning, if you think about this equation, y equals e to the x. Wait, I just did onto. I meant to say 1-to-1. Is it 1-to-1? So if it's 1-to-1, that means y equals e to the x has at most one solution for each y. And we know some values of y that make it so y equals e to the x has 0 solutions. Those are negative numbers, or 0. But if y is a positive number, like, I don't know, 4, then there's only going to be one value, one value of y that gets you, one value of x that gets you that. It's the natural log of 4. So there's only, because there's only that one value of x, that means it is 1-to-1. Okay, let's look over here with h of x equals x cubed. Graph looks like that. And you might be able to tell from just the graph if you think about it, or you might know But we could do this by just saying, how many solutions does y equals x cubed have for different values of y? Well, if I want to know what x was in terms of y, you could just take the cube root of both sides. And the cube root, you can plug in a negative number, of course. So even if your y value is like -8, then the cube root of -8 is just -2. So you can take the cube root of any number, which means that this always has at least one solution for each y, and there's at least one x for each y, and so that means it is onto. But if you want to know if it's 1 to 1, that would mean that there's at most one x. And yeah, there's only one x for each y here. You can think of it as a horizontal line test. No matter which y you pick, there's only one x that goes through that. So yeah, we can say that every y in R has a unique cube root. There's only one x for each y. Okay, let's look at this one. If you graph this, it's going to look something like this. And so it's shaped basically like a cube root, or a regular y equals x cubed graph. The only difference is if x is small near 0, it looks kind of more like a downward line there. So let's see. Is it onto? That means does every y coordinate have at least one x that goes with it? And I think you can tell yes, it's onto. Is it 1 to 1? That would mean for each y that you pick, there's only one x that goes with it. And for some values of y, that would work just fine. Like right here, if that's my value of y I pick, yeah, there's only one x that goes with that one. So that sounds good. But if my value of y is, I don't know, let's say 0, then the problem with that is that there's 3 different values of x. So it looks like if we say y is 0 and we say 0 equals x cubed minus 2x, this has 3 solutions. Which is more than 1, and you're only allowed to have one solution. So that means this is not 1 to 1. Okay, so zooming out here, we can see that we've got all 4 possibilities. You can either be neither 1 to 1 nor onto. You can be both 1 to 1 and onto, like this one. You can be 1 to 1 but not onto, or you can be onto and not 1 to 1. All 4 of those possibilities will happen, and they'll happen with linear equations too. By the way, none of what we did right now is linear algebra, because none of these are linear equations. But with linear algebra, you can get all 4 of these possibilities just the same. Now, here's example 5 on the next page. I already wrote this. This is just a rewriting of this transformation. So the transformation x maps to ax is the same thing as saying t of x equals a times x. And so we want to know if that's onto or 1 to 1. Now, t of x means the same thing as a times x. And the definition of 1 to 1 and onto that we just saw were both of the form of something about solutions of the equation ax equals b for each b In this case, B would have to be in R2. What do solutions of that look like? Is there more than one solution for each B? Is there no solution for some B? If not, then it's not onto. So anyways, we're going to investigate solutions of AX equals B the way we've been doing by thinking about, well, let's row reduce this first, and then I'll get to what to do. So to row reduce this matrix, this A is equivalent to, I'll leave the first one alone, and then do 2 times the first row plus the second row to replace the second row. Did I say 2? I meant -2 times the first row plus the second row to replace the second row. So that would be 0, 0, 1. So this has a pivot position in each row. So A itself, we can say right here, has the same pivot positions as this other matrix that it's equivalent to. And by theorem 4, that means AX equals B is consistent for all B. And the fact that it's consistent, that means there is a solution. So that means there is a value of X that will make T of X equal B for every B. So that means it's onto. Also, we want to know, does it have more than one solution? If it has more than one solution, then it's not one-to-one. And you can see because there is a column with a free variable, that means if AX equals B has a solution, then x2 could be anything here, and you could determine what x1 is based on what x2 is. And so that means there's an infinite number of solutions, and it's not one-to-one. So it is not one-to-one, but it is onto. Let's look at this one too. So again, we want to think about solutions of AX equals B. And so we can row reduce A. Oh, but hey, it's already row reduced. We got pivot positions here and here. There is not a pivot position in every row. So that means that there are vectors B that make AX equals B have no solution. So it's not onto. Because of that row. And let's think, is it one-to-one? That means does AX equals B have more than one solution? Well, if we write out the augmented matrix for this, you might already know the answer, but I'm just trying to explain it in as much detail as I can. There's your augmented matrix. And since it's already reduced, what we've got is the first variable here, x1 equals b1, x2 equals b2, and the last one says that 0 equals b3. Now it will have a solution if b3 is 0. It will have no solution if b3 is not 0, which makes it not onto. This will have, but can it have more than one solution? No, because whatever your b vector is, there's just going to be one x1 and x2 that goes with that. So that makes it one-to-one. Okay. here is a theorem. If t is a linear transformation, then t is 1 to 1 if and only if the equation t of x equals 0 has only the trivial solution. So let's prove that. Again, this is an if and only if thing here. So let's make the green statement be that t is 1 to 1, and the purple statement can be the rest of this. So if we're proving from left to right, that means we're assuming that t is 1 to 1. So what is the definition of 1 to 1? It's that for any b in the codomain, for any possible output vector, the equation t of x equals b has at most one solution for x. So if you plug in b equals 0, t of x equals 0 has at most one solution, which is what we're assuming here. And if it has at most one solution, well, we know one thing that you could plug in to any transformation and get 0 with is 0. So you must have the solution x equals 0. So that was what we're trying to prove here. All right, that was a pretty simple thing to prove. Now let's go backwards. We're going to assume this part and then prove that it's 1 to 1. So if we assume that this equation has only the trivial solution, let's see what we can do. Now, if we're trying to prove that it is 1 to 1, which is the goal, then the definition of 1 to 1 is that for any b in the codomain, t of x equals b has no solution or one solution, but it can't have more than one. So we're going to assume that we have b as any vector in the codomain. So we want to, so yeah, let's look at the different cases. There's t of x equals b has no solution, and if that's true, then we're good. Or the other case is t of x equals b has at least one solution, and we want to show that it has only one solution, not 2 or 3. So if u and v are two different solutions, then t of u equals t of v equals b, and you can use the linearity property to say that t of u minus v is the same thing as t of u minus t of v. And t of u is b, is what we're assuming there, and t of v is b, so this is the same thing as b minus b, and that gets you 0. So that means that that means that u minus v is a solution of the trivial equation. But we're assuming that this equation has only the trivial solution. So that means that the input vector that gets you the result 0, that vector must be 0, because that's the only vector we can put in and get 0 out, is the trivial solution. So and if u minus v is 0, then you can just add v to both sides of that equation, and that means u equals v. So that means if you have two solutions, that you think might be different, then it turns out they're really the same. So that means it really only has one solution. This is a general way in math. If you want to show that something is unique, that there's only one object which satisfies whatever property you're talking about, you suppose that you have two of them, and then you do some stuff to show that they must actually be equal to each other. So that's a common proof technique when you get into more advanced classes. You probably won't need it so much in community college. So in either case, t of x equals b has either 0 or it has one solution, and that's what it means to be 1 to 1. All right, here's a more important theorem that we're actually going to use all the time. We're going to say that if t from Rn to Rm is a linear transformation, with standard matrix A, then T is onto if and only if the columns of A span Rm, and T is 1 to 1 if and only if the columns of A are linearly independent. And this helps you link 1 to 1 and onto with all the other stuff we've done with matrices before. So the first part is basically a change of notation. So you maybe looked at that and said, oh, that's obvious. If so, then you're understanding linear algebra well. But if not, here are some ways of seeing how they're the same. So there's a statement, the columns of A span Rm. That means the span of the columns of A R equals Rm. That means every vector in Rm is a linear combination of the columns of A. That is another way of saying for every B in Rm, the equation A times X. Remember, A times X is a linear combination of the columns of A. That equation is consistent. And that's another way of saying the transformation T of X equals AX is onto. That's the definition of onto. So those mean the same thing. And with B, it's slightly less straightforward, but let's see. You could say the columns of A are linearly independent. What does that mean? Well, the definition of linear independence is that the equation A times X equals 0 has only the trivial solution. And theorem 12 says that if T of X equals 0 has only the trivial solution, that means it is a one-to-one transformation. That's what theorem 11 just said. This one's theorem 12. Okay, so so that's why that makes it easier, I think, to think about when a linear transformation is onto and when it's one-to-one. You can kind of use this to translate it into terms you might be more familiar with. So this is definitely an important theorem to know. So let's see. Oh yeah, this last example, I'm going to save this example for class. I think you could try a few of these right now. Maybe try to do it with A, but I'd like you guys to work on this in class. I'm going to save it as like a group activity kind of thing. So maybe hold off on it for now. Maybe try it with just one or two of them. And I will see you in class on Tuesday.